All right, I want to talk about two things in this lecture. The first is the idea of generics. And we've already used generics when we looked at linked lists from java.utility. We could declare and construct a linked list, but inside angle brackets, we had to say what kinds of things were in the list. And the reason for that is that, whether we have a linked list of integers, doubles, strings, rectangles, things like that, most of the code doesn't change, right? Really, all that changes is the declaration of the argument to the add method, right? Or, the argument to a constructor if we're constructing a node with a data value. But the actual mechanics of the code doesn't change much. And so rather than write, one linked list class for integers, another for doubles, another for strings, linked list is generic. Same thing happens with hash map, right? The idea of taking a key value pair and storing them and retrieving them and searching and deleting and so on, mostly independent of the type of data. So how does this work, right? Well, when we make our own classes, we can make them generic also. So let me make a myVector class. So let's just make a simple class for storing a 3-tuple of things. So let's just call this a class and we'll just have three things. I'll call them first, second, and third. And that's really all I need in my class to have a myVector. So let's make a main method. But let's, construct it with, I don't know, 10, 20, and 30. And let's make a toString method. And let's print out the elements individually. So, this is not a particularly useful or exciting class, but we're creating a vector with three objects inside it, integers in this case. We'll have a toString method that will print it out, convert it to a string in some reasonable comma separated way, and then we can print out the individual fields. So let's embellish our myVector class. So we've got our first, second, and third fields. I'll just go ahead and make these public so that we can access them from everywhere. Let's make a constructor with three arguments. So public myVector. And we'll construct with three arguments for second and third. And we're going to use the trick we learned about this, where we can say something like this: dot first equals first, this dot second equals second, and so on. And then we'll make our toString method. So if we try to convert our vector to a string, we'll get the first element, a comma, second element, a comma, and then our third element. All right, so that's a pretty basic class. We should be able to compile that. Need a parenthesis. And we should be able to compile main. And we can run main, and there we go. We've got a vector. That's what it looks like as a string. We can pull out the individual elements. All right, nothing really shocking going on right now. So suppose we want a vector of doubles, right? Well, we have to change this to say double. We have to change each of these to say double. But that's kind of it, right? Not much else has to change. And if we want a vector of strings, we just change this to say string, 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 and so on. So we can make the myVector class generic by specifying, hey, when you construct or declare a myVector, you have to specify a parameter. So t is the type of thing we're going to store in this vector. And then down here, instead of saying int, I can just say t. So if I construct a myVector with integer, this will say first, second, and third are integers. If I construct with a string, this will say first, second, third are strings. And then down here in the constructor argument list, I can use that parameter t. So I can compile my vector, and that should work fine. And now in my main method, I can say my vector integer v equals new my vector, put in the arguments, and then say angle bracket integer. So if I compile main, I put this in the wrong place. Alright, so if we compile main, that compiles up fine, and when we run this, it does exactly the same thing as before. Now, if I change this to say that I'm going to make a vector of doubles, then I can compile main, and it wants, doubles here. So I have to specify my arguments as doubles. And now when I run it, I see I have a vector of doubles. Now if I wanted a vector of strings, and I could put in a set of strings like that, I can compile my main program, and when I run my main program, I've got a vector of strings. Right, there's what my vector looks like with commas in between, and here's the first, second, and third element. So I don't have to keep changing my class for my vector, right? That code is exactly the same in all these cases, but I specify what kind of thing I'm going to pass to my constructor, and what kinds of thing I'm going to save in the fields of my class. And when I make a myVector, I just say, is it a myVector of strings, integers, doubles, rectangles, hash maps, right? Whatever. This can be any type of object. So that's the basic idea of a generic. And mostly we use generics, but as you develop classes, you may find yourself developing a particularly useful complex class that works with different types of data. And rather than make different classes for each of the different types, you may be able to make it generic. All right. The other thing I want to look at is class extensions. And the idea of class extension is code reuse. If we want to make a class that does a set of things, but there's already an existing class that does some of what we want to do, or does what we want to do in a slightly different way, we can start with that existing class and make changes to it. And we don't need the source code for that class. we can simply take an existing class and we can do a few things. We can say, hey, I'm going to add a new method to this class, or I'm going to add some new fields to this class, or I'm going to make my own version of a method in this existing class. And so we can override things that are in an existing class, and we can also access things that are already available in that existing class as we add and override pieces of it. So let's use our previous binary search tree as an example. So we had a myTree class, and this was wrappers around the node class, and among other things, we could do a left node right traversal, and it would do a nice print out with a new line at the end. And we had a main program that would let us add things to a tree and then call the traversal. So let's first of all modify this left node right, because if we run this program, we get a list of nodes separated by spaces on a line. Suppose we decide what we really care about is we want a left node right method that will put our list of nodes inside angle brackets. And so let's make a new version of myTree. Let's call it SuperTree. So this will be like myTree, but with a better left node right method. So we'll say class SuperTree, and we're going to say extends myTree. All right, now if we just do that, if that's all we do, we just say SuperTree is an extension of myTree, and then we go into our main program, and we say SuperTree, tree equals new SuperTree. We can compile main. That should automatically compile SuperTree for us. And then if we run main, it works exactly the same as before, right? So we don't really have to do any work to make a tree extension other than making a file with a class name.java and saying that class extends an existing class. But if we want to do more interesting things in here, we can add or modify methods in here. So let's make our own left node right method. So public void left node right, and what are we going to do here? Well, what did we do before? We said if root equals null, and then let's just print out a pair of square brackets with nothing in between, and return. Otherwise, we'll use the roots LNR method. But first, we'll print out a left bracket, and we'll print that without a new line. And at the end, we'll print out a right bracket. But in between, we'll call root.lnr. All right, so here's our updated LNR traversal method. If the root's null, we'll print out a pair of square brackets with nothing in between. Otherwise, we'll print a left bracket. We'll call the roots LNR method, and we'll print out a right bracket. So let's try compiling that. When missing slash, got us 7 errors. And this is why it's helpful to be consistent. All right, right, so here's our main method, right? We haven't changed it at all. We're still going to call LNR. Here's our entire supertree class, right? And it's got an LNR method. It refers to root, and there's no root defined anywhere in this file. It refers to root.lnr. There's no root.lnr defined anywhere in this file. But this will still work. Right, when we run this, we call LNR on an empty tree, it's a square bracket. If we call it on a full tree, it's, a set of nodes with spaces in between and a bracket at the end. So how is this working? It's working because when we say extends my tree, all the stuff that's inside my tree is available inside this class, including the root, right, which is a tree node. And we haven't declared tree node root, but the compiler knows that there's a root inside my tree, and that's what this is going to refer to. All right, so we've changed the behavior of a method here by redeclaring it inside the supertree class, and that overrides the LNR method in the original myTree class. So the original myTree class, we had a method called LNR, which did this. Well, now when we call LNR on a supertree, it's going to do this. All right, we can also add new methods to our class. So let's try this. So as a string, tree looks like, and let's just append tree to a string and see how it prints out. So if we do that, it says as a string, tree looks like supertree @ hexadecimal code. That's, what happens when you print an object if you don't have a toString method. So let's add a toString method. To a supertree. So we'll say public string to string. And our toString is just going to say this is a binary search tree whose root is, and it's going to tell us what the root is. And again, we don't have root declared anywhere in this class, but since this extends my tree, root down here refers to the root, that it inherited from the myTree class. So if we compile supertree, and I don't know if we compiled main, let's recompile main and run main, and now it says as a string, tree looks like a binary search tree whose root is, and it's giving me this funny thing. Tree node @. Right? So why is it doing this? Because tree node doesn't have a toString method, right? But if we put a toString method inside tree node, then this would print out the value of that node. And if we try to print this out before we've added anything to the string, then it tells us as a string, tree looks like a binary search tree whose root is null, because we had an empty tree to begin with. All right, so that's an example of a class extension, and we're going to use these critically when we start working with GUIs, when we start trying to create graphical elements on a frame that our Java program makes appear. If we want to put buttons, or we want to do graphing or things like that, we're going to have to use this idea of a class extension, because we don't want to write ourselves all of the pieces of the class that goes into making what's called a J-frame, right? A widget that we can look at visually and move around and resize and so on. We're going to repurpose the existing code for a JFrame, but extend it to add a few extra things to make it look and feel the way we want it to. So we'll be dealing with extensions a lot in the coming classes. All right, thanks.